Okay, let's look at potential energy now. Here I have a ball. Now you know that if I was to hold the ball up, the higher I get, the more energy it has. Okay, so the amount of gravitational potential energy is dependent upon its mass, dependent upon g, that is the acceleration due to gravity, and its height. Let's just explore those concepts a bit. I have this ball. Let's say I hold the ball about 1 meter above the ground. Okay, well the pull of gravity is the same at this location. Okay, so it's 9.8 meters per second squared. That's the value of the acceleration due to gravity. If I have this ball there and I drop it, it'll drop with a certain amount of energy, right? It has a certain stored potential energy, which gets converted to kinetic energy as it falls, right? And we'll look at that in a little bit more detail in a sec. But I drop it. If I was to get another ball, let's say a bowling ball with more mass, and I was to drop it from the same height, h, we know that h is the same, g is the same, but now all of a sudden I've increased its mass, therefore I should have increased its gravitational potential energy. And so you know if I was to get a bowling ball and drop it onto something, it has a lot more energy. So the gravitational potential energy is dependent upon the mass of the object and how high it is. Right, because g pretty much for us is going to be constant, although you will find out when you study science a bit more that it's not really constant, it decreases with altitude. But let's just say that the value is pretty much constant at 9.8. So let's do some calculations. So let's say let's draw it over here. Let's say I have a building. There we go. And I had a 2.5 kilogram ball, and the height of the building, let's say, is what shall we make it? We'll make it 105 meters. So if I was to drop that ball, right, first of all let's just calculate how much gravitational potential energy it has right up the top here. So right up the top, and we'll do this at a different color, gravitational potential energy and kinetic energy, so two of them. So up the top here, the gravitational potential energy is its mass, 2.5, times 9.8, times the height in meters, 105. And let's get our calculator out. 2.5 times 9.8 times 105, 2,572.5 joules of energy. Now, if I'm holding that still, it's not moving. So all the energy we have right at the top here is expressed in this gravitational potential energy. There is no kinetic energy. So if all of my energy is here and I've got none, that's zero. So it means the total energy I have of this whole thing is that. I can't get any more, right? I can't change it. There is a law called the conservation of energy, and this is what it is. Okay, so it cannot be created nor destroyed. So if we're starting off up here, when we're holding this ball, all the energy we have is this much. We can't make more and we can't get less. It just gets converted into another form. So what forms does it get converted into? Well, if we drop it, it starts losing height. And if we start losing height, it starts decreasing its gravitational potential energy. So let's just go down halfway and see what we get. So if we go down to halfway, we go down to 52.5 meters. So what's the gravitational potential energy at 52.5 meters? Well, let's work it out. So we know the gravitational potential energy is equal to its mass, which is the same, 2.5, 9.8, but now the height is 52.5. What is it? Let's check it out. Okay, so its energy is decreased from 2,572, and at halfway it's a lot less. What is its gravitational potential energy when it hits the ground? Well, its height is 0, So if the height is 0, anything times 0 is 0. So on the ground, its gravitational potential energy is 0 joules. Where could that energy have gone? Because we said that it can't be destroyed, it has to go somewhere. Well, it's transferred into the other type of energy, kinetic energy. So as this ball is falling, it's losing potential energy and therefore gaining kinetic energy. Let's do some calculations for kinetic energy and see if that's the case. Well, kinetic energy, the formula for kinetic energy is a half mass times velocity squared. So let's do some calculations here. Well, we'll do the kinetic energy values over here, right? So the kinetic energy up the top here, well, we said it's a half times its mass, so a half times its mass, which was 2.5. But it's not moving. Its velocity is 0. So that means it's got no energy to begin with. So that means all the energy, and that's what we said before, 0 joules. All the energy is this. So the total mechanical energy of the whole situation is that. There's no kinetic energy. I wonder what the kinetic energy is halfway down. Well, if we know that this is the total mechanical energy, and we've calculated the gravitational potential energy, then the kinetic energy must be what we start with, take away our gravitational, right? If we look up here, right? Let's just take this over here and work it out. Mechanical energy is equal to potential energy plus kinetic energy. So therefore, the kinetic energy is equal to the mechanical energy minus the potential energy. So all we have to do is get this value here and take away that, and let's see what we get. So 2572.5 take away 1286.25. Wow, look at that. It's exactly the same. So at halfway down, the kinetic energy is the same value as the gravitational potential energy. As it started at 0 and it increased to that, the gravitational potential energy started here and decreased to that. So in other words, as one was decreasing, the kinetic energy was increasing. So I wonder what the value would be down here. If the gravitational potential energy is 0, you would expect that the kinetic energy has to be all of this. So I hope that makes sense to you. Okay, a lot of maths, but just think about it. We start off with all the energy up the top. No kinetic energy, it's not moving, so that's 0. So all the energy that we have is this. As it's falling, it's starting to move. So if it's starting to move, according to our formula here, velocity, it's starting to gain kinetic energy. As it's gaining kinetic energy, the gravitational potential energy must be decreasing because the height is getting less and less and less. At halfway, we have the kinetic energy equaling the gravitational potential energy. As we go past halfway, the gravitational potential energy is getting less and less and less till it gets to 0, because at the ground, the height is 0. And that must mean that all the energy we started from in terms of potential energy must be converted to kinetic energy when it hits the ground. Okay? So, hopefully that makes sense to you, and you'll be able to do some calculations of both gravitational potential energy using this formula and mechanical energy using that formula. Here's a challenge question. If we know that halfway this energy here is equal to the gravitational potential energy and the kinetic energy, can you calculate how fast that ball is going at the halfway point? All right, I'll see you in the next video, give you the answer, and let's see if you found it out the same way as I did. All right, hope that makes sense. See you in the next video.